curve is defined implicitly, which means the y and the x are kind of trapped together. We could, of course, make y the subject, but you'd be getting inverse tan. So sometimes it's easier to deal with it as an implicit equation. We're going to do implicit differentiation here. So I'm going to use the product rule on the left-hand side. This is u, and this is v. U dash will be 2x. V dash, a little bit trickier. You basically differentiate tan as you would normally, which gives sec squared, but keep it as y. That's actually in the formula book, that tan goes to sec squared. You don't need to use the quotient rule, which would be how you would do it otherwise. But then we times by, we just stick a dy by dx in. The reason for this is that we're using the chain rule. We're differentiating the outside function, the tan, but keeping the inside the same. That's where the sec squared y comes from. And then we times by the derivative of the inside, which y is the inside, so that's where the dy by dx comes from. And now it's going to be u dash v, so that's 2x times tan y, plus uv dash, which is x squared, sec squared y dy by dx, and the right-hand side differentiated becomes 0. So you've got a couple of options here. You could make dy by dx a subject in terms of y. We're going to have to somehow, in a minute, remove the y's because the final answer is in terms of x, or you can just go straight for it now and try and make like get everything in terms of x, which is what I'm going to do, I think. I just think there's less likelihood of making a mistake. So first up, if x squared tan y is 9, that means that tan y is 9 over x squared. And I can just replace this function here by that. That just leaves us with the sec squared y. There is a relationship between sec squared and tan squared. And it's as follows. Go back to the original trig identity that you learned. Sine squared plus cos squared is 1. I'm just being brief here and not writing the arguments in. Divide through by cos squared, which gives us tan squared plus 1 is identical to sec squared. You can either learn that or you can just learn the process of getting it. There's also one where you divide by sine squared, which gives 1 plus cot squared is cosec squared. So they're really quick to obtain. Okay, we want to use this one here, which means sec squared is 1 plus tan squared, so it'll be 1 plus 9 over x squared squared. That means, what am I going to get? I'm going to get 18 over x, because this is going to cancel with this, times, oh, sorry, the tan y is now gone. So yeah, it's 2x times 9 over x squared becomes 18 over x, plus x squared, bracket 1 plus 81 over x to the 4 dy by dx is equal to 0. I think I will, I think I'll expand, right, let's just write dy by dx and then expand this bracket bit to give me x squared plus 81 over x squared. And that's going to equal minus 18 over x. And therefore dy by dx is minus 18 over x all over x squared plus 81 over x squared. I'm just going to times top and bottom by x squared. You can see in the final answer that 81's by itself, which will give me minus 18x over x to the 4 plus 81. And that is what it was looking for. Okay, not the easiest, has got to be said, but we've managed to find dy by dx by using implicit differentiation and then subbing in some trig that we knew the original equation was in terms of. In part B, we're then asked to prove that C has a point of inflection at x equals the 4th root of 27. This means we're looking for where the second derivative changes sign. When it's less than 0, it's called concave. And where it's greater than 0, it's convex. And it's where it goes from concave to convex or vice versa. Before I talk any more about that, let's find the second derivative. I'm going to need to differentiate again. So this time I'm going to call this u, this v, and the second derivative is going to be u dash v minus u v dash over v squared. The formula book gives it in terms of g and f, but it is there if you look for it. So u dash is minus 18, v dash is 4x cubed. So minus 18 times x to the 4 plus 81 minus 18x. So actually that's going to become a positive times 4x cubed all over x to the 4 plus 81 squared. Let's just tidy this up. So I'm going to get minus 18x to the 4 1458 minus 1458 then plus 72 x to the 4 and that simplifies to 54 x to the 4 minus 1458. Okay, now there's different ways to do this. Quite a good shout is just to solve it equal to 0. It's got to be said, you don't always get a point of inflection when the second derivative is 0, actually. There's different, for example, it can actually change sign without it ever equaling 0, or just because it equals 0 doesn't even guarantee a point of inflection, because it could be positive one side and it could be concave, then 0, then concave. But it's a good thing to do to get the point where it is 0, and then we can just look either side to check that, especially because this is a show that question, check that it does actually change sign. So solve d2y. Otherwise, you'd have to solve like the inequalities to find the range of values for where it's concave and where it's convex, which sometimes you might have to do, but in this case, I think it's going to be a little bit nicer. Because when it's 0, the denominator we can just ignore. It's going to be that 54 x to the 4 minus 1458 is equal to 0. That must be what it is. And therefore x to the 4 is 1458 over 54, which in fact is 27, which gives us this fourth root of 27. So now I'm just going to say when x is greater than the fourth root of 27, the second derivative, thing is we can just look at it because the bottom is always positive, then when I go above the fourth root of 27, clearly that top function is going to be greater than 0 now because x is slightly bigger than the value that caused it to be 0. So I'm just going to say, without actually calculating it, that it's going to be bigger than 0. You could put in a value if you wanted, but I think the mark scheme actually is okay with this. And when x is less than the fourth root of 27, so I'm basically saying it's changing sign. So there's a point of inflection here. Okay. Well done on your efforts here.